Okay, here's an example of one that has a little more work with it, because again, step one in solving any nonlinear inequality is to get your expression compared to 0 on the right hand side. Now that you're dealing with a fraction, something that was pretty easy with the polynomial examples, the first couple of examples, they also didn't start off being compared to 0. This one, I had to just subtract 7x from both sides, and that's no big deal with a polynomial. Same thing with the second example. I had to subtract 20x from both sides, and that's not, an outrageous amount of work with a polynomial. With fractional expressions, it's got a little extra work involved, because I can't simply subtract 1 and just, magically subtract it from the 1 in the negative 1 in the numerator. You've got to realize that you can only add and subtract fractions when they have a common denominator. So step 1 of getting this compared to 0 looks like this. You have your 3x minus 1 over x plus 6 on the left hand side. When you subtract the 1 from over here, keep in mind that minus 1 does not have the same denominator as that x plus 6. So I've got the comparison done to 0. I still want to subtract 1 from both sides, and that's done here legally. I just now need to go through the work of getting a common denominator to bring these two together. Okay, so don't make the mistake of just subtracting the 1 from the numerator, because that 1 does not currently have the matching denominator that you need. So I need to, I need to rewrite both of these so that they have denominators of x plus 6. Well, the first fraction already has that. If I want to turn the number 1 into something over x plus 6, well, if you want to think of it as 1 over 1, I multiply the bottom of this fraction by x plus 6. I've got to multiply the top by x plus 6 as well. So I'm just rewriting the number 1 here so that it has the common denominator I need to bring these two together. And again, when you do this, so that's one level of difficulty that you have to accommodate here, is to get the common denominator. Then you've got to realize that this numerator is kind of protected from that minus as it's written. When you bring these together into one fraction, which is your next logical goal in getting a common denominator, you got to be mindful of the sign changes you got to watch out for. Your first numerator is not going to have a sign change. It'll stay 3x minus 1. But this negative has to distribute to both parts of that next numerator, making it minus x minus 6. That's an easy step to forget, because you don't really see those parentheses there and you think you're only subtracting the x, but you're actually distributing this subtraction to every part of that next numerator, so that requires you to change both signs. So it took a few extra steps, but we finally, almost finally, 3x minus x is 2x, well, negative 1 minus 6 is negative 7 over x plus 6. We finally have step 1 done. We have a rational expression, a single rational expression on the left-hand side compared to 0 on the right-hand side, and the left-hand side is already factored. There's no more factoring to do in the new fraction that I've made, but this is equivalent to the original inequality. It's just now it's essential to have it compared to 0 for your sign analysis. So now I'm dealing with a rational expression. So just like in the previous example, I want to list the zeros from each part of the fraction. Now notice, this inequality does not contain the equal to part. So that means I won't include the 0 that I get from the numerator. The numerator's 0 is going to be x equals 7 halves. So I'll label that on the number line. The denominator's 0 is x equals negative 6. So both of these zeros go in order on your number line. Negative 6 is first. 7 halves comes later. 3.5 is its value. And since I do not include the value that makes it 0, I will not include the value from the numerator. And of course, you'll never include the 0 that you get from your denominator. So both of your zeros are critical points that are labeled here on the number line. Those critical points get open circles because, well, neither one gets included. So I've created 3 intervals. And I want to test my inequality for each of those intervals. So I want to see how it affects the 2x minus 7 over the x plus 6. See if this does produce something greater than or equal, or greater than 0, excuse me. And I'll just go ahead and pick my test points. Here, for this first interval, I'll just test x equals -7. So when I plug -7 in for all the x's, the left-hand side of this inequality becomes -14 minus 7 over -7 plus 6. Is that going to be greater than 0? So again, I'm looking for a positive result here. So this is -21 divided by -1. And yes, negative divided by negative is positive. So positive 21 is greater than 0. Checks out. That is true. So that means I should include every interval or any value from that interval. From -infinity up to, but not including the -6. Okay. So now for my middle interval, you're going from -6 to 3.5. So the easiest thing to check there, once again, is going to be x equals 0. Anytime you can use it, do use it. And then plug that x equals 0 into a fresh copy of your inequality expression for all the x's. All the x's here go to 0, so I'm dividing -7 by +6. I want to see, is that greater than 0? And it is not. -7/6 is not greater than 0. That is false. So that means no solutions come from the middle interval. And x equals, let's see, since this is 3.5, I'll just go ahead and test x equals 4. That's a number that's in that interval from 7/2 all the way to infinity. So plug that into a fresh copy of your inequality to check for greater than 0. All the x's become 4's, so that means I have 8 minus 7 up top over 4 plus 6 in the bottom. So I'm dividing 1 by 10. That is a positive result. You're dividing positive by positive there, and that is greater than 0. So I get a true statement on this last interval. That's what I'm looking for. So every number in that interval from 7/2 to infinity is included with the solution set. So I've tested all my intervals. That means my final solution in interval notation will be this interval that goes from -infinity up to and not including -6. So that'll be parentheses -infinity, comma, -6 parentheses. Then I'm gluing it together with this other interval, so I'll use the union symbol and then start with parentheses at 7/2, comma, to positive infinity, and that represents the solution to this particular nonlinear inequality. Okay. If you notice, I went back to the number line for the two examples of rational inequalities, because the graph analysis with rationals is a little bit tricky, because sometimes your horizontal asymptote gets so close to the x-axis it makes it really difficult to analyze the graph to see when the graph is above and below the x-axis. So the best time to use this graph method, which is really great, is on polynomial inequalities, when you don't have to worry about asymptote behavior, vertical or horizontal asymptote behavior. I mean, if you want to try one of these, one of these inequalities with the graphing method, you're welcome to, because it does work. You just have a lot more graph analysis in constructing a function that looks like this than you do a polynomial function. Okay.